going for today. The first thing I'll bring up is the test for next week. So we're a week out from the test. It happens in class time, so it'll be 12 till 12:50. We are going to switch rooms. We're going to write it out in 2038. That's a big lab, so we'll have some room to spread out there, which will be really nice. I'm going to post all the details in sort of a neatly printed sheet on Brightspace. But in the meantime, the things you probably care about, there'll be 4 questions on the test, sort of a mix between, you know, some conceptual ideas and some problems. So there's a mix. More or less, if we've covered it in class, it's fair game for the test. You know, the reason I do it in class is because it's important, and if it's important, it could be on the test. The cutoff for the test will be whatever we get to at the end of today's lecture, so that should give you plenty of time to start reviewing. There's practice material posted on Brightspace, and I will get, you know, an information sheet up on Brightspace as well. As you start to review, I certainly recommend that your lectures is your first line of study. Go through all the things we did in class and make sure you're familiar with the homework problems. I put them there because they're good practice for you to be able to absorb the material. Once you go through all the lectures and the assignment, it's probably a good idea to review the assignments and the problem session questions. So those would be good to do. And then on Brightspace, under course contents, there's midterm 1 or term test 1. I can't remember what I got it called. There are some old midterm exams under there that you can also try for practice. I did tell you can bring in a sheet of paper, a sheet of notes. I'm going to stick with that. I'm also going to give you an equation sheet. I'll post the equation sheet and the cover sheet of the test as soon as I get that test finalized. I think that's everything I can remember. Any questions? Yeah.
Do we get a sheet for the problem set?
So you passed in your problem set quiz. They'll be given back to you. Ming has them all, so I guess he'll give them back in the lab periods, so Monday and Thursday of next week. If you want it before then, just drop by and see Ming and he should be able to set you up. I posted those grades, so you can pick up the questions. And I didn't post the solutions yet. I'll put that on my to-do list. Post solutions for those quizzes. Okay. As you're getting ready for the test, it's important that when you're writing out your test answers, you show the complete answer. So if you make any assumptions, you should always write down what assumptions you're making. You should always show your equations in symbols and then show how you put the numbers in. You don't have to keep the units in the workings, but your final answer should have units. You should give your final answer generally in 3 significant digits unless something else makes more sense. I can't think of how it would, but on the off chance. You should, if there's anything that's not crystal clear, like if you make a leap in your logic, a few words explaining that leap. Fundamentally, I want you to show me that you know what you're doing. So if you communicate that, then you should do pretty well on the test, hopefully. Hope everybody does great. Okay, now I think that's everything. Any questions? No? Okay. So, last day we did a lot of stuff about electric flux. We talked about the scalar product. We finished up by saying that electric flux didn't depend on the size, shape of a Gaussian surface or the position of the charge within the Gaussian surface. But we did decide that in order to get a flux, a net flux, through a Gaussian surface, you did have to have the charge inside. That was where we ended up last time. And our Gaussian surface refers to a closed surface, like a sphere or a box or something like that, something with a volume. So we're going to extend that idea today about the charge must be inside the surface. So let's say that we have a whole bunch of charges. Some charges are outside, some charges are inside, and we have a Gaussian surface. It's not showing up there super well, so I'll just trace it with a marker. Let's say that we have a Gaussian surface that encloses some of the charges, but not all of the charges. So this blue line is our Gaussian surface. I've drawn a two-dimensional object because I have a sheet of paper. Of course, this should be a three-dimensional object, like a cube or some sort of sphere or something, but it is a closed surface. So let's start thinking about how are we going to deal with this if we want to find the net flux through this Gaussian surface. The first thing we'll remember is that there's no net electric flux due to the charges outside the surface. So they don't have any contributions at all. So if a charge is outside, it does not contribute any net flux. Okay, so right off the bat, we can get rid of those because the outside charges don't do anything. And then let's think about each of the charges inside. We know that if we only had one charge inside, the flux due to this charge would be the charge divided by epsilon naught. So each charge is responsible for making a flux through the surface. So the total flux due to each charge, so if this is charge Q1, this makes flux 1 equals Q1 divided by epsilon naught. If this is charge 2, this makes flux 2 equals Q2 over epsilon naught. If this is charge 3, this makes flux 3 equals Q3 over epsilon naught, and so on for every charge that's inside. So the total electric flux is the sum of each of those fluxes. Flux is Q over epsilon naught, so fill that in our next step. Q1 over epsilon naught plus Q2 over epsilon naught plus Q3 over epsilon naught plus dot, dot, dot. So to get the net flux, we do every charge divided by epsilon naught and add them all up. So we come to a new definition now that we used last time. So we will define an uppercase Q with ENCL, so Q enclosed, and by enclosed we mean enclosed by the Gaussian surface. This is the notation your textbook uses. Some books use Q with an IN on it to mean Q inside the Gaussian surface, so you might see some slightly different notations. Q enclosed is Q1 plus Q2 plus Q3 plus dot, 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 is the net charge inside the Gaussian surface. Okay, so our net flux is going to be the net charge divided by epsilon naught. So let's put all this together with what we know about flux. So our electric flux, we have been calculating as E dot A. And now we've said that our net flux is the net charge divided by epsilon naught. So this is called Gauss's law. To come back to calculus a little bit, this scalar product of E dot A, this is a form we can use when things are simple. If the electric field is constant, if the area is something that we know. So this is a form when we have simple cases, high degrees of symmetry. These are the cases we're going to be looking at in 1051, so this is what we're going to be doing. But it is good to know that if you didn't have a simple case with a high degree of symmetry, there is still a Gauss's law you can use, but that Gauss's law form is the integral of the electric field over the entire area. So this one is the general form. we use that when the situations are more complex. The integral form is not something we need for this course, but if you do Physics 2055, you'll get lots of experience with it there. Okay, so we'll stick with this one, but this is the one, if you Googled what is Gauss's law, this is the one you'd see, and this simplifies to this when it's a simple case. I'm going to reiterate again that electric flux is a scalar. It doesn't have direction. Flux does not go in or out, even though it can be positive or negative, so no direction here. And then the last thing I'll say, because I think this is kind of interesting, electric flux, this expression for electric flux is 1/2 of one of Maxwell's equations. So Maxwell had 4 basic equations that described electromagnetism. We're going to spend like a month talking about 1/2 of an equation. I think that's kind of interesting. Yeah, and hopefully we're going to get back around to the rest of Maxwell's equations after we do magnetism. Okay, any questions to here? No? Okay, so we're good. So let's do some examples of flux and Gauss's law here. Let's see if you get the idea. Yeah.
For this example right here, the flux is equal to the, I guess, arrows leaving and arrows coming in.
Yeah.
Wouldn't this be 0?
For this one?
Yeah.
1, 2, 3, 1, 2, 3. Yeah, for this one it would add up to be 0.
Yeah.
Just because there's an equal amount of positive and negative charge.
So if we said that on, if you gave us an example like this, could we state that without explaining Gauss's law as well, or would you prefer us to do both?
So if this was a test question and it asked what is the net flux through this surface? Yeah. So if that were the question, what's the net flux through this surface? You would go to your net flux is Q enclosed over epsilon naught. So you would need this equation.
And then just
And then you would show that your Q enclosed is equal to 0. Therefore your net flux is 0. That would be a reasonable answer to that question. Oh, we're kind of going to get to that with the example too. Okay, so let's start going through a set of examples. And I nabbed this diagram from your book because I think it's a pretty good picture. So the figure shows the electric field around a dipole. And maybe you remember your dipole is 2 small charges, equal and opposite, separated by a small distance. So we've got a plus Q and a minus Q. And we want to find the net electric flux through each of the 4 pictures shown here in the diagram. So we're going to start by asking, what is the net electric flux through surface A? Anybody want to throw an answer out there?
We found the number of lines.
Yeah, it's related to the number of lines. That's absolutely true. So let's talk about that just for a second. There are 2 ways to calculate electric flux. And the 2 ways are electric flux. Remember I said we do E dot A when things are very simple, nothing looks strange, like if your electric field is constant. Here, our electric field is not exactly constant, lots of bending. This would be a case where you would have to do the integral of E dot dA, and this would tell you essentially the number of lines penetrating this surface. You might be able to look at this and recognize that that would be a hard integral to do because the density of the lines is not uniform. So that's one way to find electric flux. The other way is Q enclosed over epsilon naught. So when you're doing flux, you have 2 choices. You can do E dot A, or you can do charge divided by epsilon naught. They're both valid, they both give the same answer. It's just usually one way is easier than the other. So if we look at this way, this says Q enclosed by epsilon naught. What tends to be the hard part about this problem is identifying what do we mean by Q enclosed. Where it's a new topic, it just tends to be tangly in your head. So what you do is you look at the circle you draw and you just ask what charge is inside that surface. Okay? I guess maybe now that becomes an easier question. What charge is inside the surface? Plus Q. Okay, so our net electric flux, Q enclosed divided by epsilon naught. Q enclosed is plus Q divided by epsilon naught. And then we're done. Okay. If you had some serious math chops, you could do the integral and you'd get the same answer. Okay. I'm not going to claim that I would be able to do that integral. I'm not sure that I could. That's really complicated. Okay, questions? Ready to move on to the next picture? So maybe it's going to get easier from here. I think I only posted one slide for all of you. I printed it off on 4 slides just so it doesn't get messy. So let's look at surface B next. So this was for surface A. For surface B, I'll trace B. What do we think about the net electric flux through surface B?
Negative Q.
Yeah, okay, sounds like we're getting the idea. So it's Q enclosed over epsilon naught. Q enclosed means how much charge is inside the circle we drew. There's only one charge inside there, that's the negative one, minus Q over epsilon naught.
So is the total flux zero because the number of lines outward is equal to inward?
Wait, the total flux through what is 0?
For this shape.
Which
for,
shape?
For A and B.
No, for A, the total flux is this,
And B.
and for B, the total flux is this, because it's
So-
whatever charge is inside the surface.
So the net flux of A and B.
Well, that brings us to our next shape. So let's move on to our next shape. So you've always got to look so closely at that surface. So our next one is what is the net electric flux through surface C? So you draw your surface C. Our net electric flux through surface C is Q enclosed divided by epsilon naught. Now we ask how much charge is inside this surface. So there's 2 charges inside. You get the total charge by adding them up. Minus Q plus Q divided by epsilon naught minus plus is a 0. For this one, you could do a line counting approach here if you like that idea. If you count the number of lines going out, it's exactly equal to the number of lines going in, so that would confirm your answer there. And then we have one last surface. Okay, through surface D, let's circle surface D. Net electric flux through surface D equals, what do we think about through surface D?
0,
0, why 0?
because there's no charge.
Because there's no charge inside. So we look inside surface D, we ask what's in there. There's nothing in there, there's no charges in there. So Q enclosed over epsilon naught. There are no charges at all inside surface D. 0 over epsilon naught equals 0. This is not an uncommon type of test question. To show a distribution of charges, show a Gaussian surface, find the net flux through the surface. An old switcheroo I did one time was I gave a set of charges and I said draw a Gaussian surface through which the net flux is something, right? So if it was Q over epsilon naught, you would have to draw surface A. If it was 0, you could draw surface C or D. So that would be a way I could ask that question backwards. Okay, questions here? Okay, fantastic. So the next example we'll do puts a few things together here. So a charge of 170 microcoulombs is at the center of a cube of edge 80 centimeters. No other charges are nearby. So I drew a cube in 3D. I've got a charge at the center. So about right there. So there's our charge cube. And we want to do three things. Draw the electric field around the point charge. That's okay, we know how to do that one. Find the total flux through each face of the cube, and find the total flux through the whole surface of the cube. So part A, let's do that one first. Let's draw the electric field lines. I'm going to do my best to draw in 3D here. So one line goes up, one goes down, one goes right, one goes left, one goes forward, one goes backwards. That's kind of it. So that's my attempt at a 3D drawing. So there are my electric field lines. I'm going to label that B. Part B, find the net electric flux through one face of the cube. So let's just think about this one for a moment. So that's part A done. Part B is find the flux. Net electric flux is. If I want it through one face of the cube, this is back to some of the first flux examples we did. We were doing E dot A, and in all those examples we had a constant electric field. This time, our electric field is radial, so the electric field points out like this, but our surface is planar, right? So this is a weird electric field. It's a radial electric field with a plane surface. To me, this just screams complicated. Okay, so this is hard to do. So what I'm going to do is I'm going to switch up the order, and I'm going to do part C first. Then I'm going to wonder if part C helps me answer part B. And I asked this question this way on purpose, just to get you used to seeing that there can be different ways to think about a problem. So let's skip B for a moment, and let's jump ahead to part C. So, equals part. So let's skip to part C. My net electric flux through the cube. Two ways to do it, because we have this cube, which is, all X, Y, and Z, and the radial electric field. That's complicated. This would be one of those times you would have to use the integral form. So you could do it that way. It would be really hard. So we could also do flux Q enclosed over epsilon naught. That one tends to be the easiest way to do it, and we'll try that way anytime we can. Okay, so the flux through the entire cube is Q enclosed over epsilon naught. Q enclosed is 170 times 10 to the minus 6 coulombs, divided by epsilon naught, 8.85 times 10 to the minus 12. Coulombs squared over newtons meters squared gives us 1.97 times 10 to the 7 newtons meters squared over coulombs. Okay, so part C was piece of cake. We've got this surface. We know that flux is charge over epsilon naught. Now let's go back to the idea of a cube. A cube has 6 faces. Our charge is at the center. So this has a lot of symmetry, right? So everything is exactly the same. Our charge is right dead at the center. The electric field lines spread out evenly. So every face has to be the same, right? Because it's at the center and the way it spreads out. So coming back to B, so the cube, 6 faces, charge at center, that's symmetric. Therefore, the flux, the electric flux through one face is 1/6 of the total electric flux through the entire cube. .320 times 10 to the 7 newtons per coulomb times meters squared. Okay, questions? Okay, so that takes us to finishing up Gauss's law. Actually, I'm gonna call this point the cutoff for our test. I don't have anything on the test that's gonna take us past here. So, any questions to hear? Keep going. So we're going to start applying Gauss's law to conductors. We're going to do that for a little while. Before we get started on that, there are some properties of a conductor that we should work through and establish. So for a little while, we're going to talk about properties of a conductor, but we need to set the baseline that we're talking about conductors in what we call electrostatic equilibrium. So for the next little while, until we get to circuits, we're talking about conductors in electrostatic equilibrium. So the electro part means there are charges. The static part means they are not moving, they're still. So V is equal to 0. And the equilibrium part is the same equilibrium from physics 1050 or 1020. It means your acceleration is 0. So this is what we're going to be talking about. So conductors will have charges. Those charges are not going to be moving. They're going to be completely in equilibrium. This might get us to start thinking about if your A is 0, what's your force and what's your field. These are things we're going to start talking about. Here's the list of our 4 properties. We're going to go through the first 3 in this chapter, and for the 4th one, we're going to come back to that when we do the electric potential chapter. So we're going to go through the first 3 first, and then come back to number 4. So these will all be written down again as we go through them. So our property number 1 is that the electric field is 0 inside a conductor. And what's implied here, and I'm probably not going to write it down every time, is electric field is 0 inside a conductor in electrostatic equilibrium. So you can just assume that a phrase always applies. So let's think about why that has to be true. Every single in the charge in the conductor has to have acceleration equals 0. That's the equilibrium part. We know that force is equal to mass times acceleration. That's our Newton's second law. If A is 0, then our force is 0. Okay, so if A is 0, your net force has to be 0. Well, we also know that electric field is the force per unit charge. The force is 0, that divided by the charge is equal to 0. You can sort of think about it the flip way too. If the electric field is not 0, then the force is not 0, then the acceleration is not 0, which means it's moving, which means it's not in electrostatic equilibrium. So you can think the reverse direction if you prefer to kind of put your head that way. This result feels like this one is easy to understand if you have your conductor by itself, not inside an external field. So this one kind of makes sense if there's nothing around it. But we do have electric fields everywhere. So what if you have your electric field and what if you have your conductor and there's an electric field outside? What does that do? So let's try and look at that on our picture. So let's say that there's no electric field. So no external field. What happens in that case is that your conductor is full of charges, but they're all just kind of randomly placed around. More or less like this. Okay, so they're randomly placed around, and they will position themselves so that they're in equilibrium so they don't move around. So everything here is random. If we introduce an external field, let's call that external electric field, E with an EXT on it. Let's draw that external field. let's say it points to the right, because I have to pick some direction. So there's my external electric field. Let's think about what happens to the charges inside the conductor when they're in that external field. So a positive charge will feel a force to the right. It's going to get pulled to the right. A negative charge will feel a force to the left. It will get pulled to the left. We now have a separation of charges where one side is positive and one side is negative. That's going to create an internal electric field. And what happens is that enough charges will move until the net electric field is 0. So let's get that in a set of notes. So what happens is that charges feel an electric force, or charges experience an electric force. The positive and negative charges separate due to that force. So the force makes them move around and it makes the charges separate. That creates an internal field. And that internal field will cancel with that external field, or they'll sum to 0. So this one, property number 1, that electric field is 0 inside a conductor. This is something you're just supposed to know off the top of your head. So if I give you a test question and I say we have this aluminum sphere in electrostatic equilibrium, find the electric field inside the sphere, all you need to write down E equals 0 inside a conductor. Okay, so this is a result that we accept and we know. The only time you would have to do any work on this sort of a problem would be if I said prove why the electric field inside a conductor is 0. Okay, so justify it. So that's a result you're just supposed to know. Any questions here? Okay, let's do the next property. So our property number 2 says that if a conductor in electrostatic equilibrium carries any excess charge or any net charge, all of that net charge will be on the surface or surfaces of the conductor. So if a conductor has a net charge, it all spreads to the surface. So let's think about how we're going to show that that's true. I'm going to trace my conductor. So it's just this weird shaped blob. So there's my conductor. Then I know I want to apply Gauss's law. To apply Gauss's law, I should think about a Gaussian surface. I'm going to choose my Gaussian surface really carefully. I'm trying to think about what's happening on the surface of the conductor. So I'm going to draw a Gaussian surface that's just inside the surface of the conductor. So I'm going to draw it so it's really close to the surface. So I've got a little tiny bit of separation between the lines. That's more of a visualization thing. But really my Gaussian surface is right up against the surface of the conductor. So this one is the conductor. And this one is the Gaussian surface. So I'm drawing a Gaussian surface just inside the surface of the conductor. Just inside means really close. You know, in math speak, there's an infinitely small distance between the Gaussian surface and this physical surface of the conductor. So now let's ask, what's the electric field inside the conductor? So that's the one we know off the top of our heads. We know that the electric field inside the conductor is equal to 0. Okay, so that's our first property. So our electric field in here equals 0. And it has to equal 0 because we're in the side a conductor in electrostatic equilibrium. So if we think about Gauss's law, whether we use the plane symmetric one or the integral form, doesn't matter. The electric field is 0, so this whole bit, 0 times anything gives us 0, is equal to Q enclosed divided by epsilon naught. So the electric field inside the Gaussian surface, inside the conductor, is equal to 0, so the flux is 0, so the Q enclosed equals 0. So the net charge enclosed by the Gaussian surface is 0. So now we sort of have a little thing to recognize. If there's no charge inside the Gaussian surface, and there is a charge on the conductor, where does the charge have to be? It has to be outside the surface, right? It can either be inside or outside. It's not inside, so it has to be outside. Therefore, all charge is outside the Gaussian surface, which means it is on the physical surface of the conductor. This makes sense when you think physically about charges. If you have a bunch of positive charges on a conductor, those charges are going to repel each other, right? So they're going to get pushed away from each other. They'll be repelled, pushed away until they can get as far apart as possible. The place they can be the furthest apart is when they're on the surface. Okay, so it lines up physically with what's happening with the charges. Okay, are we good to here? Okay, so now we have time to do our demo. So we're going to do an application of property 1 and property 2. So there's no field inside of a conductor, and all the charge must be on the surface of the conductor. And let's ask the question, what if you had a hole inside your conductor? So I guess most people have their phones right next to them, so this is going to be a phone activity. So sometimes when you have your cell phone, you drop your signal. Like once in a while a text won't come through or a phone call won't come through. So we're going to look at what's going on there. Let's do the activity first, and then we'll do the explanation afterwards. Does anybody need any tinfoil? You can do it with a friend, or you can do it solo. If you're by yourself, take 2 pieces of tinfoil. If you're with a friend, take 2 pieces between you and your friend. So I'll give you the bunch and then just pass it around, please. Oh, did you need some too? And the deal is, if you're working with a friend, it has to be a friend you're comfortable sharing your phone number with. I don't know if that's a big deal with the youth today. I'm not here to judge. So, what you're going to do is, if you're with a pal, one of you wraps your phone in tinfoil, and the other doesn't wrap their phone in tinfoil. Oh, sorry, before we get started, please turn your ringtones up as loud and as obnoxious as it goes. So we got to get it nice and loud because we want to be able to hear. Give it a test if you want to. Nobody makes fun of anybody else's ringtone. It's all good. Okay, then the choices are, if you're with a pal, one of you wraps up your phone. If you're not with a pal, if you're flying solo, text a friend who gets back to you right away, and ask your friend to give you a call in about 30 seconds. I can do this with my oldest kid. She's never longer than 30 seconds from answering a text from me. I'm not going to, but I could. So then take your phone and wrap it nicely. Okay, lots of good contact. You might have to use 2 pieces of tinfoil because some of it is old and beat up. So text somebody to give you a call, or share your phone number with your friend sitting next to you. Either or, doesn't matter. Okay, so text your pal to call you in a moment, and then wrap it up really nice using 2 or 3 layers, whatever you need to do so that it's a nice, good closed contact. As soon as you're wrapped up, wait for your friend to call you.
Can you set a timer instead?
No, it's not gonna work with a timer. It's gotta be external calling you.
So we gotta wait for our friend to call us.
Okay, so wrap it better. If you got a signal come through, you can just try and wrap it better. It will work eventually. Phones are changing.
I didn't top off my phone number, so it's not gonna be.
Okay. For most people, if it's wrapped up nice and tight, the phone is not going to ring.
I guess we'll call you. That's pretty tight.
Yeah. Yeah, you can try another couple of pieces of foil. There is a new technology that they're working on to get around this. So it's pretty fun.
It also uses, if it can't get an initial signal, I have Wi-Fi calls, so that might be.
No, you shouldn't get Wi-Fi either.
So I thought Wi-Fi signal passes through better than radio.
It probably passes better.
So it might be one of the reasons.
Yeah, which could be why you need a little bit more. So if it's calling, you will hear it, right? Because you turned your phone up. So for most people, it didn't come through. Okay, so not for everybody. The phones are changing these days, and some signal will get through, some won't. If you wrap it up in more foil, it eventually won't get through. And this is a result of the properties we just talked about. So to get a phone call, you need an electric signal. You need an electric field to get through. My phone is wrapped in a conductor. The electric field inside the conductor is 0. No field, no signal. This whole effect is called shielding. And the foil that we're wrapping it in, that's called a Faraday cage, left over from Michael Faraday. Okay, everybody unwrap and we'll buzz and ring for a while as your missed calls come through. And then we'll just kind of talk a little bit more about it. So, good, I'll go on that. So the applications of this, wrapping your phone in tinfoil and having somebody call it, that's not a whole lot more than just like a party trick, although it is a good party trick. Anybody use an RFID wallet, maybe especially when you travel? Some people usually have one of those. So apparently what the bad guys, whoever the bad guys are, can do is they can walk up to your wallet or your purse, they can scan it, and they can get the magnetic strips off the back of your credit cards or the information off your passport. They just have a scanning app on their phone and they can read the information on your cards. So people put their cards and their passports in an RFID wallet, which is basically just a tinfoil bag, and it protects those strips. Anybody order electronic parts off the internet? Usually we get a handful of people who order stuff like that off the internet. A lot of those electronic parts are very sensitive to the scans that airports do. When they go through some of the x-ray machines, it can just fry the circuitry that you ordered. So that's why it always comes in what's called a static bag. So basically it's a tinfoil bag. Nothing here on campus, but some exam halls or like musical halls and things like that, those are all completely shielded, so participants inside can't get a phone signal, so the phones don't go off during an exam or during a performance. So kind of some of the big ones have that. Most computer rooms, like the big computer rooms that run all the computing in industries and on campus, most of those are completely shielded as well. That applies to the computer room here on campus over in the Henrietta Harvey building. So the entire room is shielded, so that if there's outside electric interference, like during electrical storms, the computers inside don't get affected by those varying signals. So it's kind of a big thing. Okay, so this is called shielding. And we put the objects in the conductor is called a Faraday cage, and it'll be shielded from external electric fields. Okay, the next thing I wanted to do was use Gauss's law inside and outside of a conductor. This is kind of a big chunk to do at one time. Does anybody object if we quit 5 minutes early? Okay, so we'll start here on Monday, and you can have a peek ahead if you want to. It's all done in your textbook.